Okay, I think that worked. Did you guys get like the message thing? Maybe, or it did it before, so it's probably fine. Okay, cool. So, hey everyone, thanks for showing up. I guess let's go into what I'm here to do, and hopefully what you guys are here to do as well. So, first of all, who am I? What am I doing here? What are my qualifications to be teaching anyone about how to do anything? Well, one, I'm Paul. Hopefully that was pretty clear because my name thing says Paul Staley. I made a little tiny rocket engine. There it is. There it is melting. It only melted a little bit and everything ended up okay. But that's an important qualification to the whole rocket engine thing. In addition to that, I'm a shop tech around here. So I've always been a kind of manufacturing focused guy. I like machining and stuff. Right now, I'm also at an internship where I'm doing some kind of like rocketry related things. And most of all, like, as it turns out, there are a bunch of people who are working on rocket related stuff at Cal Poly right now. And I'm super excited about that. And my hope is that some of the stuff I can do, I can hand off to you guys, whether you are actively working on one of the people who's building a rocket engine or just think this stuff is cool, or have no idea what you think is cool and just showed up and want to see what it's like. And my hope here is that I can hit something for all of you. So, important distinction here is what I'm not good at and what I'm not trying to do here. Making a rocket engine is something that often sounds like really technically complicated and crazy. In my opinion, like that's not entirely true. And my like evidence for that is primarily I'm not a super technical guy. I'm not standing here telling you guys, okay, I figured out some efficient way to make a rocket engine, so an incredible way to do any of this stuff that's like above or beyond what anyone else could do. I'm not really, really good at doing any crazy or wild analysis, and I don't think you need to build a rocket engine here. So just right off the bat, that's not my claim. There might be things I say analytically or technically that aren't completely correct, and maybe I don't have like a super PhD level understanding of some things, but my point here isn't that I'm an expert in that. My point here is that what I probably am very good at, and my hope is that I'm in somewhat of a unique position to transfer this information to you, is how, like practically how to make a tiny little rocket engine. My process for making mine took a really, really long time, and I made a lot of mistakes. And I saw a lot of other people trying to do a similar thing and falling off a cliff and never making it. So the hope here is that I can take all those little bits of information that you really can't find just by looking for it and give them to you guys, so that if you want to make a rocket engine, or if you just want to become more comfortable with like how this whole deal works, you don't have to make some of the mistakes I did. You know, that there's this general idea that like people fail to make rocket engines because they're obsessed with analysis or they overanalyze like crazy. And that's somewhat true, but it's also just really hard to know. Like the hardest part is to know where and where you can't say like, hey, we're going to cheat a little bit here. We're not going to do this calculation. We're going to say this is good enough. And again, that's information that you can't really find in a textbook. And I think I found out enough of that, that my hope is what I have here is an ability to give you information that will turn into something pretty cool. So what exactly this is going to be a very practical discussion about what building a small liquid rocket engine looks like, or what I personally think it should and could look like. So we're going to go practically through each subsystem or group of components on the rocket engine. The goal being kind of to fill gaps in your knowledge if you're already someone who has a ton of experience with this, give you a really good basic ground level understanding if you're someone who is kind of really new to all of it. And the product here, and like the way that I want to do this, is by actually designing the entire rocket engine here in 10 or, you know, maybe a little bit more 45-minute sessions, including like all the CAD, all the calculations, everything right here. And this is going to be like a really little tiny one, and I'm hoping to have some input from you guys. But, you know, if it works, I really, truly do think that that's something that can be done. The goal being to demonstrate that, well, it literally isn't that hard to do, and you can kind of see it getting built right in front of your eyes. because there are a lot of people who are interested in this with really wide ranges of expertise, it's very possible that a lot of the stuff I'm going to go over here is either going to be like a bit above your head or way below what you understand. I just ask you guys to kind of bear with me on that. I'm super, super interested in helping you, whoever you are, and whatever your exact thing is. And I'd be happy to work one-on-one or answer any kind of questions. But this I do kind of have to tailor so that everybody can get something out of it. So, you know, especially for people who know a lot about this, might not be the most like technically intensive thing at the beginning, but I'm very, very confident that if you stick through this, there are those weird little holes and super important things that you just can't get any other way. So I've also just made a Discord, especially for those of you who are watching this as a recording. There's literally nothing in it. It's not like an actual Discord. But that is an awesome place to ask me questions if you don't happen to be in any kind of media with me already. I'd also be happy to shoot anyone who wants my number, and you can text me anytime. So I'll also post recordings of this on that Discord. Encourage you guys to join, and obviously ask any questions you have here as well. But I am willing to sit down, hop in VC, or just text out a really long answer to anything you are wondering about this. At the end of the day, I really want more people to learn about this, and I really want more people to understand that it's not nearly as bad as they think, and you can make some really, really cool stuff pretty easily. All right, cool. So the exact way this is going to look like is kind of two parts. The first part is going to be what might be a little bit more boring. Some people might love it. I don't know. I would be bored by it. I wouldn't show up for it. But one, which is what we're going to do right now, is a kind of broad overview of the anatomy of what the whole thing looks like. And that's going to feel a little bit eclectic and like chaotic, but promise there is a method to the madness here. And there are just a few of those kind of purely theoretical, not practical. This is what the structure looks like. This is what these terms mean. And this is the intuitive grounding behind all of this that I think is important to get through. And then the next two are going to be talking about requirements and propellants. And those are, again, hopefully somewhat interesting. My goal is to make it interesting, but at the end of the day, not hard design. So stick through it with me, and, you know, at the end of the day, hopefully we'll be able to do some cool stuff. I've already got plans as we design this thing. If anyone's interested in actually making it, the hope is that it'll be cheap and easy enough for someone with a yellow tag to make. Whether or not you're in a club or something, got some time on a lathe, I want to make, like you, if you stick around here, in a position to build components for rocket engine. So hopefully that's kind of the little light at the end of the tunnel for sitting through this, which is the boring part. Okay, so what I want to start off with is kind of a little thought experiment. And this is, again, going to be not crazy deep. A lot of you are probably going to know where this is going. And my ask is just to, sit back, think, see if you can maybe like imagine it in a slightly different way than you have before, or just get a little bit more intuitive insight into it. That is the idea. And so what I'd ask you to do is to imagine an astronaut with a shotgun and another one sitting in front of a big old rock, or whatever that 1-ton thing is. Anyway, both of these two guys have a goal, and that is to go quickly. So both of them want to accelerate. They're floating in space. Now both of them do something. The one with the shotgun pulls the trigger, and the one standing next to the block pushes really hard off of block. And I'm sure you can imagine a scenario in which these two guys end up going about the same speed in the opposite direction. The kick from that shotgun is going to push the astronaut with the shotgun backwards, and pushing off of a heavy object is going to push you backwards as well. I'm sure you can also imagine in a vacuum that the other object would float off in the opposite direction. Now, the bullet is going a lot faster than the 1-ton rock, and that's kind of the key here. That's not as like clear a thing as you might expect, because it leads to some interesting conclusions. Primarily, that one bullet is relatively light. It can get you going just as fast as pushing off of a 1-ton block. Now, if you redefine that in the idea that both of these astronauts have the goal to go fast, and they've got to bring something up with them to let them go fast. One of them brought 1 ton of stuff and went like a couple miles an hour. The other one brought like 1 shotgun shell and can go the same speed. And I'm sure, again, if you take that a step further and imagine you put them on an even playing field and tell both of these astronauts, okay, you can bring the same amount of mass up. Let's see who goes faster. Now the one with the shotgun has a ton of shells sitting around, can shoot them all, and is going to end up going really, really, really fast. And the reason for that is the speed of the mass. That's the only difference here. If you're in space or on the ground and you can push something away from you quickly, the faster you can push it away, the more quickly you end up going as a result. And again, I'm sure like if you take in dynamics or even statics, you understand that and you can write out the equations behind it. But the point is that even in a very abstract sense, it kind of makes sense. And the next thing to do is to look at rockets in that context. Rockets are just another solution to this problem. The shotgun is one, pushing off of a rock is another, and a rocket is a third one. Again, the only goal here is to take some mass and get it going really, really fast. Rockets happen to be a solution to this problem that we're interested in because of 3 main things. One, they can speed up the mass pretty good. It goes really quick, probably faster than the bullet even. They can speed up a lot of it at a time, and they're not super heavy. So there are a lot of things which fulfill some but not all of these, like a water rocket, where you just fill up pressurized water and shoot it up into the sky. It can move a lot of mass and is pretty light, but the mass doesn't end up going very fast. And there are types of engines called like ion engines, which can get mass moving like very at significant fractions of the speed of light. But we don't see them sitting on rocket engines or jet planes because they can't do very much of it at one time. So there's nothing special about a rocket in terms of what it does. It's just this kind of nice happy medium between these 3 things that does kind of the exact same thing the shotgun did. You know, the shotgun isn't contributing to the speed directly. You know, he's not throwing the shotgun, he's not pushing off of it. In fact, on some level, it's extra mass sitting around. The astronaut's heavier now carrying this thing, but it gives you the opportunity to accelerate other mass you have around and end up a lot faster. So, okay, let's extrapolate this idea to, also, sorry if I sound weird. I'm recovering from a cold. That's probably why I also look like I'm in hell right now. But okay. Next thing to look at is the first bit of terminology. And there are 3 key things that I want to look at here, or actually 2. I don't care about the third one. We'll talk about that in a second. The first characteristic is, like I said before, rockets are good because they speed mass up pretty fast. In the analogy with the shotgun, that would be equivalent to saying the shotgun's good at speeding the astronaut up because the speed of the shotgun slug is high. And when we're flying rockets, we call that exit velocity, which is just the speed that the mass is going at. And like we just talked about, and as hopefully you understand intuitively, the faster the mass goes, the more efficiently you can speed yourself up. So we also use that as a measure of the efficiency of a rocket engine and call it specific impulse. And again, that's one of those words which is like, sounds complicated and weird. Sorry. Okay, give me like 2 seconds to grab a glass of water. Sorry.
I'm going to use this opportunity to quickly say, if you're here for Polyprop, if you could put your preferred email in the chat, please do. Thank you.
Okay, hopefully I don't sound like a medieval peasant dying of some weird disease now. Let's see. So specific impulse. That's a weird word. It's one of those kind of like technically sounding words, but all it is exit velocity times a constant. We're not going to worry about what that constant is, but it's like a direct scale of exit velocity. So whenever you hear someone say specific impulse, all they're talking about is how fast the mass is accelerated. Now, the second characteristic is that it can speed up a lot of mass at one time. And to bring that back to the analogy we're using, that would be equivalent to how many of the shotgun shells are the astronaut cycling through? Like, how much of this stuff can he get out? You know, does it take him 1 minute every time he fires one of these things, or does it take him an hour? And what we call that is m dot, or the mass flow rate. And that is, you know, the dot, if you're familiar, is just indicates a rate of change. So it's the rate of change of mass out of the system. And you can also imagine a kind of third thing from these. Again, if we go back to the astronaut, and our question is, okay, like how fast is he going to be speeding up? Is it going to take him like 3 hours to get really fast, or is he going to be able to do it in like a couple minutes? And it's a combination of how fast it's going, how fast that shotgun shell is going, and how many he can fire. In the case of a rocket, how high the exit velocity is, and how much mass you're flowing through at that exit velocity. And in fact, you can literally just multiply the two of them together. And that brings us to our first little equation. And actually, the real only one that you need to care about for now. And that is that F, or the thrust that comes out of a rocket engine, is equal to m dot, or the mass flowing through it, times the velocity at which it's going. So thrust is pretty simple. And notice that we've got three kind of characteristics here. And, you know, if I pick any two of these, I can just algebraically solve for the other one. So this is a kind of little system we've got, and we can grab two and then get the other ones. So if I know m dot and thrust, I automatically know what the exit velocity is. These three things are like fully constrained to each other. All right, so honestly, that's literally all that makes a rocket work. That's pretty much all of the math and like, I mean, it's not really math you need to know for now. Now let's actually get a little bit more general and talk about what a rocket engine does. Because it's a good solution to this problem. How is it a solution to the problem? And I break it down into three factors. One, it takes some number of chemicals, and we call those propellants, and it puts them in a chamber. And a chamber just being some kind of vessel where they go. It then initiates a chemical reaction, which we generally think of as combustion, but it could be other stuff. If you've got baking soda and vinegar, you put them in a bottle and you mix them together, that's a rocket. And it turns them into a lot of gas. So the mass is staying the same, but suddenly we've got a lot of gas. And we've got a lot of gas built up in this small chamber. Okay, so now we take that chamber and we're going to poke a small hole in it. I mean, we've poked the hole before, but if you imagine the chamber filled with gas and you imagine a hole through it, a lot of gas is going to shoot out that hole. And more importantly, it's going to shoot out fast. And like we just discussed, efficiency and speed are the exact same thing in terms of how fast you end up going when all that mass is gone. So all that gas shoots out through the tiny hole and speeds the rocket up. So here's some examples of things which fulfill all of those conditions. One is baking soda and vinegar. Another is a solid rocket. You put the parts in before, and they are solid, but then you initiate a chemical reaction. It builds up a lot of hot gas and shoots it out a tiny hole. A hybrid rocket's another type of rocket you might be familiar with, and that kind of rocket, will operate by having some solid fuel, some liquid fuel, mixing them and firing the combination. There are also monopropellant rockets, which only use one. talk about that later maybe. And then liquid bipropellants, which is what we are going to be focusing on today and forever. Liquid bipropellant is a rocket where one, they combust in a chamber and then escape through the nozzle. There is some kind of injector, which is a strategic way of getting the propellants into the chamber. And there's some large system sitting behind it, which pressurizes those propellants and shoots them in. So again, liquid, when we say liquid, we just mean that our propellants, the two chemicals we're using, are liquids. Or often when one's a liquid and one's a gas, you still say liquid. The distinction is more between solid and liquid than between like gas and liquid. And then bipropellant means there's two of them. We've got two of these chemicals. So let's go straight into chamber geometry, which is this thing. I'm sure you guys have all seen this thing, and they look pretty complicated. It looks like there's a lot behind it, but I've labeled two things, and those are literally the only two things you need to determine the geometry of the entire chamber. Might feel pretty weird, but it's absolutely true. One is the diameter of the throat, and the other one is how much pressure is building up. You can imagine if that throat was really, really tiny and, you know, I lit off a bunch of explosive inside of it, it would build a ton of pressure. But if I had a massive throat and I lit off a lot of explosive, not a ton of pressure would form. So let's break this thing down into a couple sections because we can simplify this even more. So first of all, the diverging section. This is something that's idealized. It can be calculated. This is not something you take and you stick into some CFD program and iterate to find. You can mathematically calculate and derive a contour, which is objectively the best contour for doing what we need to do with it. We'll go later into what exactly it does. But the key point here is that you can calculate an ideal curve, and it does exist if you know the throat diameter, which is, again, that condition that we're driving with. The chamber pressure that we already mentioned before is another thing that we need to know. You do also need to know the ambient pressure or the pressure outside the rocket, but I'm not really going to consider that a separate characteristic because you can, you know, like you can pretty easily just point it wherever you happen to be and say, okay, that's the ambient pressure. And that'll make more sense when we actually do some of these calculations. Key takeaway is that when you know everything else, the curve will follow. You don't need any CEA or anything crazy to do this. The whole other part literally doesn't matter. From a theoretical perspective, it can be anything you want. That other part of the contour, that expanding part, is like very rigidly defined by crazy complex math. The other side is like, okay, there has to be enough room and like it has to have a good curve so weird stuff doesn't happen. But those are like totally practical. It's literally all practical. And so an example, again, theoretically, all of these chambers will perform in the exact same way. Now, hopefully you can imagine that in practice, that's not at all what would happen. If I like started shooting explosives into these and lighting them, they would not work very well. But it's not because like you could point at some thermochemical issue with what's going on. It's because, and you can use complicated words to describe it, you can use complicated calculations to prove it, but at the end of the day, it's because you didn't give a good shape for the fuel to burn well. Notice though that in all three of these, that diverging part is exactly the same. That's because that is a mathematically driven thing. And when we do talk about the chamber in its own presentation, you'll be able to learn a little bit more about what exactly is driving that. But the point is, one is complicated math, but it's like online calculator math. If you've got the equations, it doesn't matter how good you are at engineering, you can solve it. And the other part is practical stuff we'll talk about later. And there are some pretty easy guidelines you can use. Okay, so that all might not seem like much, but it's actually already enough to completely define an entire combustion chamber and rocket engine. I like to break it down into these 4 parameters. And the only thing really I want you to get out of this whole presentation is if you know what these 4 things are, and you understand something about, I'm going to tell in a second, you are going to be golden. So The first one is thrust, and the second one is m dot. And if you recall, we had these two in that equation with exit velocity or ISP. Which means if my goal is to fully constrain the engine, I could have switched either of these with ISP or exit velocity. It's just that the thrust and the mass flow rate are much more convenient to us. You know, like exit velocity is something that's a little bit difficult to conceptualize and calculate. So we're going to go with the two that like matter. And remember, the fact that I have these two as parameters you need to know automatically indicates that exit velocity is known, it's fixed. Cool. So the other two are chamber pressure, which we talked a little bit about. And then in terms of like how exactly you do go about setting that one, that ends up being a little bit more, it's not complicated, but it's somewhat hand wavy and weird. There's some tricks and rules to it, but nothing crazy complicated, no wild analysis. And then throat diameter. So those bottom two are going to pretty much fix the geometry, and those top two are pretty much going to fix the performance. And the interesting thing is, it's not like these are two groups of things you need to know. With any two of these constrained, so if you somehow find, say, I pick a thrust I like, and then I know the m dot or the mass flow rate that my feed system can provide, I'm done designing the rocket engine in terms of those parameters. I've fully fixed the chamber. There's no other data you need to know. There are hundreds of little different characteristics that you can have about the rocket engine. We'll go into some of them, but if you know two of these four, the entire engine suddenly becomes set in stone. And the weird thing is you can know any two. You could say, pick your thrust and pick your throat diameter, and then the other two would follow. It doesn't have to be any specific combinations. So that's a pretty important thing. But the way we design is by selecting the two of them that we are most interested in. And the hard part is, okay, so what do I actually want those two to be? Because it's not just like, oh, now I've calculated these two. The other key thing is, well, if you haven't fixed two yet, there's no like analysis you can do. It's not a fully constrained system. So the first two, you totally have to get numbers somewhere other than analyzing the system because the system doesn't exist yet. And then as soon as you have those two, the system's done, it exists, it's fully constrained, which is kind of nice. Okay, and so before we move on to talking about what the injector looks like, I do want to briefly note something because there was no other great way to put it. There are probably going to be lots of little out of place things here, but just bear with me on it. I'm sure this feels kind of like a random smattering of information again, but it's just stuff that wouldn't fit particularly well when we deep dive on the individual things. So one thing that everyone always asks about, and is another important thing that the chamber does, I didn't want to discount, is cool the rocket engine. And so I just wanted to give an overview of like some ways that that's done. And again, no need to like take notes or anything on all of this. If I'm moving quickly, it's because all I expect or think is necessary or important is that you've like heard the term or like, oh, I kind of heard of that thing. And then if I spend more time on it, the hope is that you remember it without having to take notes or anything. So definitely don't feel like if I'm rushing through stuff like this, it's like, I need to remember all of that because it's not that important. So for one thing, you can make it uncooled and just not fire it for very long, or use some absolutely crazy metals and fire it for a very long time. Another option is regenerative, which is like, hey, I've got a massive tank of really, really cold fuel, because in big, like real rockets, the fuel is like liquid. It's like liquid oxygen, which is incredibly cold. So like, oh, let's run that around the engine before we use it, and it's going to cool it off all on its own, which is a very nice way of doing things, but can be pretty complicated, especially for a student team. Ablative, if you've ever seen like those heat tiles they have on like space capsules that come down and kind of burn off and use up the heat, you can do a similar thing on the inside of a nozzle, make it out of something similar to graphite, where a small layer gets insanely hot and then it just burns off and leaves, and then you get the next layer insanely hot, That gives you a lot more time firing the rocket. And then film cooling is also common, which is a kind of like, hey, we've got all this fuel, why don't we do something with it? And what you do there is you've got a lot of burning fuel in the center of the chamber, and you can imagine a way that you could kind of spray fuel that's not burning as quickly around the whole outside of it and cool it off. Of course, there are ups and downs with all of this. I don't know exactly how we'll proceed with this kind of design I'm hoping to make here, but that's all for that at the moment. Anyway, let's move to the injector. The injector is a component of the rocket engine that's driven very much by practical considerations. Its job is to make sure combustion happens. You know, in an ideal world, you just like stick equal number of moles in the chamber of like two chemicals, and then combustion just magically happens. In the real world, the two propellants actually need to be mixed like very, very well for stuff to happen. Or I don't mean like idealized versus real, but it's a degree of idealization. So it's going to atomize them, which means break them into really tiny droplets, mix them, which means mix them, and distribute them across the chamber, which also just means distribute them across the chamber because you want the combustion happening everywhere. So let's look at an example. If I poke two holes at the back of the chamber and just flood my fuel, which I'm showing here in blue, through one, and my oxygen or oxidizer in green in another. And we're going to talk more about propellants next time or the time after that. So if you're not super familiar with like the terminology here, that's totally okay. Just know it's a bipropellant engine. We've got two. If we shoot them through and they go really, really far before they start mixing, they're only going to be burning at the very end. And you can see and imagine that a lot of the unburnt stuff is going to be shooting out the end of the rocket, and the fire just isn't going to be happening well. Like there's no like super crazy technical part of that. It's just you can see it, you can imagine it, it wouldn't burn good, and we want it to burn good. So a good injector is something like this. If you can imagine two sprays, like two little streams that are sprayed incredibly fast and they hit each other, they're gonna like blow apart, mix super, super, super well, and combustion is gonna be able to happen immediately or close to it. So I'm gonna show you now a few styles that people use, but I think it's really, really important that you don't go like crazy and get super attached to any of these or think that these are like groupings out of anything other than, hey, these things look similar, let's give them a name and a category. Most real engines use a mixture of these. You'll be able to find 2 or even 3 or 4 of these types inside the engine, all operating because of different things. And also, if you think in your head, and I encourage you to do this after we're done, like, okay, I've got like really high 2 pressurized liquids, and I want to mix them really, really well. And I can do it by like drilling holes or making some geometry that like blasts sheets of them into each other or like hits them into each other. Or, you know, if you can imagine it and it seems like it would mix 2 liquids really well, there's no like special rocket thing. We're just trying to mix 2 liquids. And if you can think of it and you can think, hey, that would work pretty well, I almost guarantee you it would work pretty well, even if you can't sort it in perfectly into one of these few styles. Okay, so the first way that other people have gone about it is with something called a shower head. And that's just, you take a ton of little holes, you put the fuel through half of them, and you put the oxidizer through half of them. And I changed the colors here. There's no fire, and it just like was easier for contrast. But the point is these are 2 liquids. And you can see, even though they're not like hitting each other and mixing or anything crazy like that, overall, they're pretty like they're like kind of interleaved together. They're distributed relatively evenly, and they're close enough that they would burn. Another way some people do it is by shooting them at each other. You can imagine 2 high pressure streams of anything shooting at each other is going to mix them up really, really well. And this is one of the more common styles and solutions to this problem. Another style, which can be used to describe a lot of different things, is by using a sheet or sheet-like flow of liquid, often in the middle. So if you've ever seen like those I don't know, like a hose where it's got the cone spray mode and it can kind of spray a fine sheet of stuff. You spray a fine sheet of one thing and then you just blast it from above with the other one. And there are tons of different ways and geometries you can do this, but that's something people have also used. Another pretty cool type doesn't actually, because everything up to this point has used like tiny little holes to get everything fast and make them kind of hit each other. This one doesn't use that. And it's really, really hard to draw this. So like, if you're interested in this, I very much encourage you to go look it up yourself. But it's kind of like, if you can imagine those water slide things at water parks where you go into some big like bowl and you swirl around in it. And you imagine you put like 50 people all swirling around one direction in that bowl. And then you put like another one above it with everyone swirling the other direction. And then you like let the people swirling the other direction like fall onto the one swirling the first direction. And like everybody just hits each other. That'd be awesome. And the people would get mixed together super, super well. That's kind of the idea behind this. But again, the point is that like, unlike some things that are fixed very hard, we're just trying to mix stuff together. If you come up with a design that mixes stuff together, that's the whole idea behind it, not to like hit some specific category. Use your beautiful imagination. And also, it's very likely if you're here that you're interested, at least now, in using one gaseous propellant. If you don't really know what that means, it's likely that if you ever are interested in making a rocket engine, you will off the bat be interested in making gaseous one. And those mix really, really easily. So in a lot of the things we're going to be talking about here, it's somewhat of a non-issue. You can kind of get away with a lot. So not worth stressing too much about it. Okay, so I think that's probably enough background for the injector. Now we're going to pretty quickly go through fuel system and some test stand stuff. And this is going to feel like pretty fast and not super deep. And that's because, again, I'm trying to give an overview here and then like as much non-practical information as I can, but with like feed system and test stand, almost everything ends up being practical. So it is important. We'll talk more about it. But for now, let's just give a quick overview of that stuff. So remember one thing about the feed system, it's that it's all about controlling pressure, and that pressure is a resource. You have a certain amount of pressure because you've used something to build pressure, and we'll talk about that next slide, but almost everything in the rocket is going to reduce that pressure. Either because it's just a loss, there's some weird friction happening and the pressure is just disappearing. You can exchange it for flow, and you can exchange it for chamber pressure. What that kind of means is at the end of the day, the pressure is going to end up being whatever it is outside, because it's going to get shot out there and very quickly become that pressure. So what happens to your starting point? What happens to whatever pressure your propellants happen to be at the beginning is the result of this kind of ladder where things move down it. And how you build the beginning pressure to start off with. Oh, and I did just want to mention, so one thing you can use it for, as you can hopefully see on that little tiny weird graph thing, is chamber. And that was one of our, that was one of those parameters. So you can, so like one of the ways that we can start looking into, okay, so what is our chamber pressure actually going to be is how much pressure we have left over from our system, because you can see that final drop to ambient, it's all going to be that chamber pressure. And if you think about that for a second, it might make a little bit more sense. And then also in the injector, we just talked about how we want things going really fast so that they mix well. And right here, you know, pressure is something you can exchange for making things go really fast. Okay, so how you get pressure, there are a few different ways. One is a turbo pump, which is a pump capable of creating extremely high pressure and extremely high flow with blades. It's a complicated word. It just means a bladed pump. It's more like a fan than a pump in terms of the way it moves stuff, or not like a fan, like a ceiling fan, but like a, okay, never mind. Forget I said that. But a turbo pump, we generally don't do too much stuff on because it's more difficult than the entire rest of the engine put together, which isn't to say it's not a cool project, but it's kind of out of the scope of what we're doing here. Another option is pressure fed, which is what we're going to be talking about. That is where you have some tank that's filled with an inert gas or your actual fuel or oxidizer. You hook that up to your system and it goes. Another little side note, which is worth noting, is self-pressurized, where some propellants actually kind of pressurize themselves. If you put them in a vessel, they just build pressure on their own. That's very specific to one, actually, which is nitrous. And that's something we can talk more about in the propellant selection one as well. So anyway, the only other important point about pressure is that when I say like pick chamber pressure, you're not actually picking it. Like, you're not in control here. It's an insanely complicated system where everything is a feedback loop with every single other thing. Everything directly affects itself. You cannot solve it analytically. And some of the components are complex enough that it effectively prohibits you solving it computationally. I am not aware. Yeah, it's legitimately very hard to solve even computationally, and a lot of companies who make rockets don't do it, and that's even very new for the ones who are. But the point is, we are kind of at a loss in terms of predicting the exact things, but that's nice because that lets us get away with just kind of assuming everything's the worst and building our system to that. So we can't know exactly how the system's going to perform. When you turn it on, all of these things are going to reach their own equilibrium, and hopefully it's close to the one you predicted. But you can definitely say, okay, I know the worst case scenario for my chamber pressure. This is the highest it would ever be. This is the most flow I would ever need. I know the worst case scenario for this thing. I know the worst case scenario for this thing. And let's just assume they all happen at once. And that is something you can do. And that's a way you can kind of get along this really terrifying problem of figuring out some of these very, very weird feedback loops. So just to keep in mind when we talk about, say, the most common example is picking a chamber pressure, or like deciding, oh, I'm going to run my rocket at this chamber pressure. I just want to like make you guys aware, so I'm not teaching you to say things which will make people say, actually, that the rocket picks the chamber pressure. You can say, oh, my design point was this because I know I can reach that, but you can't say I set the chamber pressure. You set one thing at the very beginning of this kind of cascade, and then the cascade forms, it changes, it moves dynamically however it wants. Okay, cool. So takeaways, you can just design so that you have excess because you're never going to know exactly how much you need. As long as your design point is consistent across everything, it's going to be okay. And then just make sure baked into your system is a way to make adjustments. But yeah, that is pretty broad. And now we're going to move on to what that system actually looks like and just go through some components that I think are pretty frequently used, and just some terms that are important to know off the top of your head. One is regulator. A regulator is like a valve. Some people would say that it is used to set a specific pressure. And that's true under like some very specific circumstances, but those circumstances aren't often really that much in effect. In a rocket, honestly, a better way to think about it is just like a valve that you can set how far open or closed it is. So it's kind of a way of restricting flow, and sometimes it'll also restrict pressure. Now, the reason I say because you are scared is because the cylinders where we might get our, say, oxygen in are at like 3000 psi, and none of us have any business hooking that directly up to anything. So a regulator is full of losses. It's just kind of a massive drop in pressure for not much gain, except for, oh, we want to be safe with this. So that's why those exist on the system. In this little diagram I'm going to build here, though, I want you to think of that little bottle icon as high pressure nitrogen. So that's an inert gas. It's not going to be one of our propellants. It's not going to burn or anything, but it's going to help us because we're going to attach a pressure vessel to it. And So what we can do now is take that vessel, which is just any kind of container, fill it halfway up with fuel, some liquid fuel like kerosene or alcohol. And then when you turn on the regulator, you're going to push that stuff down. You're going to push it down. You're going to push it through whatever pipes you want, and you're going to push it into your injector. Assume you guys can read. Do not make one on the fiber winder. Please do not make a pressure vessel on the fiber winder. None of us will be able to build rockets if you try and make pressure vessels on the fiber winder. I will help you get pressure vessels and get you any pressure vessel you want for pretty cheap. Talk to me. Don't make your own pressure vessels. Okay, another little component that there's some explanation people talk about a lot, so I thought I'd mention it, is a check valve. It's just a one-way valve. It just makes sure that things are going in the direction that you wanted them to go. They're generally not used to actually prevent things from going that other direction, because you want to design the system so that if the check valve wasn't there, nothing bad would like be going the wrong way. But it's a nice safety, because yeah, if you have a pressure vessel and instead of nitrogen above the fuel, you have oxygen, it's all going to blow up and then you just have a bomb, which, and then, yeah, definitely no one would be building rockets anymore after that. Cool. Last little component I just want to mention here is the control valve, which you need because you want to be able to control the rocket. There are, people call them main valves or propellant valves as well. They are the primary valve, which is automatically turned on and off to introduce stuff into the system. Cool. There are a couple other little bits that a feed system does as well that I thought are worth mentioning, but didn't really go anywhere else. One is purging. So in addition to just pushing our propellants, a feed system can help by using that same nitrogen gas, the example I just mentioned, and taking that gas and selectively pushing it through parts of your system. You can imagine if there's some fuel sitting in a pipe and you don't want fuel in that pipe, you can build a feed system so that when you open some specific valve, it rushes nitrogen through that pipe and displaces the fuel. It should also be able to do some basic safety functions like getting rid of any pressure in the system without you having to stand in front of it, and filling and draining the fuel either in an emergency or just because that's kind of something you need to be able to do easily to run a rocket properly. Okay, so some very brief notes on test stand. It does a few things that are pretty obvious. It'll control the massive fire coming out of the engine. It will strap it down to the ground. It will separate the fire triangle. And by fire triangle, if you've heard of it, I mean spark, oxidizer, and fuel. If those three all combine, or not necessarily spark, but ignition source, if they all combine, bad stuff happens. So a test stand can be a nice little like physical divider between these things. It stops the rocket moving around except in one direction, which is up. We do want it to not go up, but we want it stopped going up by some kind of load cell or something so we can measure how badly it wants to go up. And so the test stand's job is to put it in a position where we can tell how badly it wants to go up. The test stand's not stopping it, but it's still not going to do that. It also provides a nice housing for all the other systems. Here are some examples of some test stands. The two pictures on the left are the front and back of mine. The one in the middle is a common one you'll see out in the desert. And the last one is Boston undergrad research or rocket team, whatever they're called. That is theirs. There are a lot of practical considerations for whether it's vertical or horizontal, whether it's a large wide stand or it's on an I-beam. But as long as you're familiar with these basic slides, if you notice, all of them have some way that it could theoretically slide. The one in the middle has a sled that it goes up and down on. The horizontal one, it's a little bit harder to see, but it also has a sled. Mine, you can see kind of 4 linear bearings that it would theoretically be able to slide on as well. You can't really see the load cell or how mine is going, but I promise it's on there. I'm not actually in slow, so I can't take good photos. And then last little bit, which is just going to be like a minute, is electronics, because this is worth a much broader discussion some other time. But the electronics are effectively a way that we can time and advance our valves. If you don't know electronics, it's something that you'll have to figure out if you're interested in building a rocket engine. That's also something I would be more than happy to help you with, and I'm sure you could find anyone else as well. So one key goal of the electrical system is to actually set the fire going. The two main ways that we do that is actually having something burning inside the chamber, which is called pyrotechnic. And the other option is a spark gap, like a igniter or a actual like car spark plug. Though you need a pretty strong, powerful arc to do that. Hypergolics are chemicals which are so insanely reactive that when they touch each other, they combust without any added heat necessary. They're an excellent ignition source, but they all generally like tend to kill you, like not just because they explode when they touch everything, like they also just happen to be like kill you otherwise chemicals, which is pretty wild. At my internship, there was like a building where they were doing some work with them, and they had like red warning lights like a mile away, and it was like quiet and empty like within a mile of that building, and just no one could like even go near it, and everyone was like, those people are crazy. So yeah, do it in your cool. Find some, buy some hydrazine, pour it on the floor, see what happens, send me the video. That's the takeaway there. The other key thing an electronic system can do, and you often expect it to do, is to see how close you are to the values you predicted so that you can assess and tune the engine, and also confirm, oh, okay, we're using this system to monitor the sensors and know that the system is safe to approach. I'd say there are three things that most people will stick on them, which are thrust, the pressures right before the injector, which helps you with a lot of calculations, and the actual chamber pressure you're running at. These will help you like launch the rocket or fire it. Stuff happens, and it's like, okay, well, was that good or bad, or should I change something? And the electronics will help you do all of that. So, cool. That is pretty much it. It's a little bit past 7. The stuff I wanted to recap is relatively quick, so if you've got a couple more minutes, I'll do that briefly. But if not, thanks for coming around. Just to go over the stuff one more brief time though, for those of you who are interested. 1, there are 4 major parameters of this system. 1 is thrust, which we have also fixed in an equation with m dot and the velocity or efficiency of the engine. 2, or actually 3 now because I mentioned m dot, or the mass flow rate. 3 is chamber pressure, which is the pressure in the chamber, and is one of the more difficult to find ones, but luckily something we can point at and say, hey, I'm going to say it's this, and then do calculations from there. And then throat diameter, which is the other piece we need to fully define and fix our geometry. So yeah, like I was saying, exactly 2 of these need to be fixed, and that's an important thing. The injector is just anything that mixes propellants super well, atomizes them, crashes them together. There are style groups, but like, use your imagination, go crazy. The goal is to mix fluids, not follow a prescribed like textbook, these are the 4 things, because that's not how it works in the real world either. The feed system delivers pressure and flow. All of the pressure will end up at atmospheric. It's going to get used up somewhere, and it's up to you to try and minimize it getting used up in losses, maximize it getting used up in chamber pressure, because we'll talk about it more, but chamber pressure is a good thing. And, you know, try and get as much flow in places where you do want flow, like through your injector going really fast so the streams hit each other. You cannot predict the equilibrium conditions of the rocket, and you cannot set them, but you can calculate conditions that are so bad they're kind of impossible, and say, hey, these are impossibly bad predictions, and these are impossibly bad conditions, and I know my rocket could still somehow function in them. I know my feed system could still provide enough pressure in this case. So I know it's definitely going to be good no matter what the real world's end up being. And then finally, the test stand, like I said like 5 minutes ago, fixes the engine in space, isolates the components from each other so they don't blow up, and houses the other systems. And then electronics are responsible for a lot. I literally just said those, so I don't know why that's a separate slide. Okay, yeah, cool. So that is pretty much all I had. Sorry, I'm a little bit over by now. Hope that was like marginally interested. Full disclosure, I was planning on doing a little more polish on the weekend, but I got insanely sick. And so sorry if it was a little bit hectic. Hopefully I'll get better at presenting. But next up, we're going to be going over requirements and goals, which sounds incredibly lame. And I almost didn't want to do it, but I honestly, the more I think about it, is one of the places where I think I have the most information that's like hard to find other places. And I truly think I've got a way of going about it that will almost guarantee you success if you truly follow it. And this really is one of those places where, weirdly enough, I think like most rockets that fail, or student rockets that fail, it's because of the requirements. It fails really early on, and it's not because of those obvious like reasons that you would think. So I am pretty excited to like kind of give you guys my take on all of this, and maybe not super interesting, but I think I've got a pretty good system, and I think it'd be really cool if some people followed it a bit. So that's first real design step. I'm sure there's some stuff I skipped over. I'm sure there's tons of questions that there still are. So hop on that Discord if you got the thing. If people want the link and don't have it, I can put it in the chat. Actually, I'll probably do that anyway. I don't know how to go back to a specific slide. God. But yeah, okay, here, I'll just end that.
Adam already put it in the chat, actually.
I got you on that one.
Okay, you got it? Sweet. Cool.
Yep. And for anybody who is looking for it, currently it's up at all the way at the very top.
Yeah. Cool. Neat. Well, thank you guys so much for coming out here. If you know anyone who might be interested, let them know about the recording. I'll post it on there. Encourage them to come around. And yeah, I'm sure this will get even more polished and smooth as we go. But any questions at all about literally any of this, whether it's practical, like how to actually do this stuff, hit me up on Discord. I'd love to talk about it literally anytime. Cool. I'm going to hang around here in case anyone actually has anything to say in this very exact instant. But
I also
and say bye. Yeah.
I'll also quickly say, for the people who are interested